Okay, everybody. So it's my great pleasure today. All right, we still have to pass off some balance, I guess. Okay, so it's my great pleasure to be introducing Santosh Nagarakatte. I always say Santosh. So I've known Santosh for 5 years now. I guess we were interns at Microsoft Research at the same time, and you know, I guess I was sort of more of a like focused. I want to do OS. I want to be in the OS group, and here's Santosh, who's primarily an architect. A guy at the time was working in the formal methods team, doing concurrency bug detection and sort of working on applying formal methods to basically serious systems programming problems, right? So if you've ever had to debug a race condition, for instance, it's a really painful thing to deal with, and so this is a pretty bold problem. And since then, over the time that I've known Santosh, he's just continued to sort of work on these, both sort of bringing together technologies from sort of disparate areas of computer science, as well as just tackling some really bold problems that span architecture, PL, and formal methods. So anyways, today he's going to tell us about formally verifying the LLVM compiler, which is, in case you don't know, is a very widely used compiler, including it's the default compiler backing Xcode, Apple's development environment. So this is a very significant result, as well as some other work with memory safety. So with that, we'll hand off this talk to Santosh and take it from here.
Yeah, thanks, Ron, for the introduction. So the best way to summarize my research is, I'm a systems builder. I build systems, but I'm enamored by formal methods, that I try to use formal methods in whatever I build. So today I'm going to talk about two results from two latest results. Like one is on memory safety. How do you make C and C++ programs work correctly? And this project actually let us build a verified compiler. So when I mean verified compiler, a compiler whose implementation comes with a proof of correctness saying that it completely satisfies the specification. So one of the things I generally encourage everyone attending my talk is to ask questions. Like if you don't understand anything, ask questions. Like I like to be interactive. So the goal we set out to solve long back was to make C and C++ safe and secure. And if you ask anyone why are we addressing this problem, lack of memory safety is one of the fundamental reasons why we have lots and lots of security vulnerabilities. And you may ask, like C, come on, C was designed in 1970s, we still use it, isn't this a solved problem? So if you just look at the latest vulnerability reports, just in the last 2 weeks, we have had some serious security vulnerabilities. Both using view buffer overflows and use after free vulnerabilities. Okay, so and if you dig up a bit more, you see in the last year or so, we have had more than 1,000 such vulnerabilities. Okay, so C has been around, it's widely used. Some of the software where we see vulnerabilities are things which we use daily. And these are security critical, right? So why is it that we have not solved this problem even after these vulnerabilities existing for a long time? So one of the reasons is, look at this picture. So look at the weak link in this picture. So this plastic strap holding your fence is the weak link in this picture. So we have been addressing we're proposing lots of solutions and they're providing patchwork solutions to it. And the fundamental reason we don't have complete security is because we don't have memory safety, which would avoid all these vulnerabilities. So we have been working on this project for a long time. So memory safety has two components. One is protection against buffer overflows, which is you want to prevent a pointer from accessing anything beyond the region it can legally point to. And you also want to prevent a pointer from accessing locations that have been deallocated. Long back we started this project. So as Ron mentioned, I come from a hardware background. So let's design something in hardware. So we designed a prototype called Hardbond, which did pointer-based checking. I'll describe what pointer-based checking later in my talk. and invested lots of hardware. And we said we can provide protection against buffer overflows at about 10%. Then come on, like at the end of the day, we want our solutions to be used by industrial vendors. If you propose lots of hardware, like Intel is not going to build it, or AMD is not going to build it. So what we realized from this effort was there are the key insights which can be used with a compiler-based prototype. So we proposed software in PLDI, where we said, let's leverage the compiler. Compiler has lots of information. Let's perform this using the compiler. So pointer-based checking, and it provides comprehensive protection against all buffer overflows. The overhead is about 75%, still higher, but still usable. Like let's say you have a large production software that you want to test at the data stages, and you want to test for buffer overflows, you can run it. So there's a factor of, there's an order of magnitude difference in the performance overheads reduced from like 30x with Valgrind to 75%. And then we coupled this with another add-on to SoftBound, which provides pointer-based checking, but also gives you protection against use after free errors. And again, at the end of the day, what you need to take away is, with leveraging the compiler, you can reduce the overhead of retrofitting memory safety to about 2x. It's 100% overhead. So some people say this is higher, and some people say, oh, this is good enough. So again, it depends on which class of people you belong to, but at the end of the day, we want to make everyone use our tools. So leveraging all these tools, we built a prototype called Watchdog, which makes very localized, simple localized changes in the hardware, but still hardware intensive. And it provides comprehensive safety. And this has been the lineage of the work. And what I'm going to talk about today is how we explore the hardware-software continuum to provide comprehensive memory safety. So ideally, what anyone wants is we want to provide safety, complete safety, with zero performance overhead, zero investment in extra hardware. That would be an ideal goal. So, but there is no free lunch, right? So what we have shown till now is like there is SoftBound and sets which use stock compilers and provide comprehensive safety at about 2x overhead. And then there are hardware intensive skills which we have proposed, which provides reasonable safety with invasive hardware. So what I'm going to talk about today is a hybrid solution which leverages the compiler significantly and then provides comprehensive safety at about 20% overhead with only 4 instructions added to your ISA. You're adding just 4 extra instructions to your ISA, and you have comprehensive safety. Of course, you need to recompile your program to make it work with use this instruction. Yes?
So is adding instructions an easier sell than modifying the semantics of existing stuff?
So adding instructions, so if you look at the x86 instruction set, like every year Intel adds like about 50 instructions, like SSE2 instructions, AVX instructions which were added like just in the last few months. So adding instructions is much more easier than building a whole new structures. Like if you don't have additional structures in your hardware, it's much more easier to add instructions. But the most importantly, why you need to care about this talk is because Intel has announced memory protection extensions exactly similar to our work in the last 3 months. So Intel memory protection extensions which provide protection against buffer overflows uses the same approach, and it's going to come out on chip in 2016 in the Skylake processor. Okay, so one thing you need to take away from all this work is you leverage the compiler. Compiler has lots of information, let's design stuff over the compiler. But this made us ask a question, how do you say compiler is correct? All we have is, this is a compiler the rendering is. Anyway, so this made us ask the question, so we are using the compiler to perform the transformation and do interesting things. So we have an algorithm, we implement it in the compiler. But how do you test the algorithm is correct? And this problem asks us to design mechanisms so that we can show that the compiler implementation that we designed for memory safety is correct. And that's where we realize this effort is analogous to building a verified compiler. So what we have done in the last few years is we have built parts of the LLVM compiler in a proof assistant. We have formalized semantics. There are lots of challenges in doing this, and we have shown that if people invest time in it, we can actually build a compiler whose implementation comes with a proof of correctness. And there are lots of challenges which directs my future research, which is primarily how do you make it practical for any compiler writer to use this. So there are two parts. In the first part, I'm going to talk about memory safety, and I don't know how many of you are familiar, but most of you have written, I presume most of you have written some C programs. I'll give you a quick background on what memory safety is and what are the techniques which we are going to use to retrofit memory safety. So let me ask the first question. So many of you have written programs. Let's say you have a pointer void star C in your program. What can this point to? So this can point to anything. It could be a pointer to an integer, it could be pointed to an array, it could be pointed to a structure, it could be pointed to a subfield in a structure, it could be out of bounds pointer. Again, 100 things, right? So now if you want to check, at some point in your program, let's say a module, you get void star C, you want to check this pointer as valid, accessing this does not cause any memory corruption. Performing the checking is not the hard part. The hard part is what information do you maintain so that you can perform the check. So how do you propagate this information? That's the key challenge. So what we have proposed in our research is, rather than maintaining information with each memory location, provide each pointer some metadata, which provides a view of memory. Each pointer has a view of memory that it can legally access. So each pointer has some metadata which provides a view of memory that the pointer can legally access. So now the challenge is, what metadata do we maintain so that we can protect against buffer overflows and protect against use after 3 years? And how do we propagate them? So to address the buffer overflow, it's pretty simple, right? Like a pointer points to an allocation. So a pointer you have to maintain the start of the allocation and the end of the allocation. And for bound safety, all we do is each pointer maintains the start of the allocation and the end of the allocation. In this case, there are 3 pointers, both pointing to the same allocated object, and they have the same metadata. But D is a pointer which has been either involved in pointer arithmetic or indexing operation, points to a location which is beyond the region that the pointer can point to. And now, before every dereference, you check that the pointer is within bounds. And in this case, D is outside the bounds of the region the pointer can point to, you would prevent such an access. Okay? So now, how do you detect use after 3 years? So what we said, there were 2 aspects to memory safety. One is protection from bounds errors, and the second aspect is protection from use after 3 years. And we just figured out, we just maintain bounds information and propagate it. We can check it before every memory access. We can provide protection against buffer overflows. Now, how do we provide protection against use after 3 years? So when does a use after 3 error? So use after 3 error arises, you make an allocation, you make a pointer point to it, and then free the location, and then you have an alias pointer which can point to it. When you free it, like, you don't clear all other pointers that can potentially point to that location, right? So when you dereference an alias pointer that has been potentially allocated, you will have a use after 3 allocation. So just accessing deallocated locations is not a problem. But one of the fundamental principles in computer science is locality. What does your memory manager do when you deallocate? It tries to reuse memory because of the cache lines want to reuse the same location. So when you reuse memory, the deallocated location may be allocated to a different object. Using the dangling pointer, you can corrupt arbitrary data structures. And this is how Google servers were attacked in 2010 in China. It exploited a dangling pointer vulnerability to create a security threat. So let me give you a simple scheme that would prevent such attacks. So what you need to do is provide a unique identifier on every allocation. Okay? So in this case, there are 2 pointers as before, A and B, which are pointing to this allocation, and you are providing a unique identifier, 1 and 2. So both are pointing to the same allocation, so they both have the same identifier. And you also maintain a set of valid identifiers, right? And now when you free this, you remove the identifier associated with the allocation from the set of valid identifiers. So here we have removed one from the set of valid identifiers. Now if you try to dereference B has an identifier 1, it's not present in the set of valid identifiers, you would raise an exception, right? And now let's say our memory manager, some program is reusing the memory and allocating another object. In this case, you reallocate the same location, potentially to a different object. So your memory manager is providing a new unique identifier. Okay? So as long as you dereference just C, your access is valid because C has identifier 2 and 2 is present in the set of valid identifiers. But on the other hand, when you try to dereference B, B has identifier 1, 1 is not there in the set of valid identifiers, and you would prevent such an error. Okay, so what have we done? By maintaining identifier metadata and bounds metadata, we have shown you can provide protection against both user-to-free errors and bounds errors. But the devil is in the details, right? So now, how do you implement? Like what we need to do before every memory access is we need to check this identifier is there in a set of valid identifiers. How do you do a set lookup? Any takers quick? So you have a set of objects and you want to check if a particular object is present in the set or not. I see lots of students, like someone would have implemented a set hash table. So what are we saying right now is before every memory access, do a hash table lookup. This is going to be crazy, right? Like your program had 100 accesses, now a hash table lookup before every memory access. And each hash table lookup is a translation and then some memory accesses, key and tag checking. That's about 10 access, let's say 10 memory accesses there. So you have 10x overhead right there. So another question we need to think about is how do we design the identifier checking so that we eliminate this checks. And the next thing is, we have been very abstract about where are we storing this metadata. Like we said, pointer has metadata, right? Where do we store this metadata? So one suggestion is like, let's just make every pointer fact. Like every pointer has 4 fields with it: base, bound, and identifier. So what is one common feature of C code? So let's say you're getting a network packet from some device. Like your device reading a device register, and you are interpreting it as a structure. What is the first operation you perform when you do this? A typecast, right? So when you have a typecast, you can arbitrarily corrupt metadata. Now you need to now you have additional mechanisms to protect the metadata. So one of the schemes we identified is that you don't store the metadata together with a pointer. You store the metadata on the side in a disjoint metadata space. So you have a pointer. In this example, you have pointer B2 stored at location 0xA, and we store the metadata for this pointer in a disjoint metadata space corresponding to address 0xA. Right? So by maintaining the pointer on the side in a disjoint metadata space, you protect the metadata. A cache only manufactures pointers. It cannot touch them, cannot corrupt the metadata. And the cool thing we realized was you don't have to maintain metadata for everything. What is important is pointers. And you need to check pointers. So we maintain metadata only for pointers in the disjoint metadata space. So one of the principles in 101 of computer architecture is your program should have minimal linked data structures. So it won't work well with your prefetchers, it won't work well with your execution engine. So if you apply that principle, what it means is programs tend to operate more on data than on linked data structures. So your program apparently should have some linked data structures to maintain various invariants and various data structures. But program generally tends to operate on data. So as long as your program operates on data and has very few pointers in memory, the metadata overheads are negligent. So you store the metadata only when you have pointers. You only have pointers in memory, or only when you load pointers from memory. So now the question is, where do you, we said, abstractly, we said we can have the metadata in a disjoint metadata space. Now the question is, where do you allocate this metadata, right? So what we do essentially is store this metadata in some part of virtual memory. Now, what we need to do, before this pointer is being dereferenced, we need to translate this address to a metadata address. And when this pointer is being loaded, we also load the metadata from the disjoint metadata address space. Okay? So, what have we seen till now? We have seen that to provide protection from bounds overflows, you need bounds metadata. And to provide protection against use of free errors, we need identifier metadata. But we said, just maintaining identifier metadata can probably slow down your program. And the third thing is we need to protect the metadata, so we have disjoint metadata, so which can hurt locality. Now you don't get the metadata quickly, right? So now, what are the mitigation techniques that you can propose to avoid this? The first thing we use is the problem we have at hand is we don't want to perform a hash table lookup before every memory access. Expensive. We want to make it as cheap as possible for identifier metadata. To do this, we split the identifier metadata into two parts: an address part called the log and the key part. Okay? And the invariant we maintain is the key associated with the pointer is equal to the key at the log associated with the pointer. So this is best explained by an analogy. Let's say we have a landlord. Okay? So landlord has an apartment to rent. And there's a tenant who wants to sign the lease. When the tenant signs the lease, the landlord assigns a new lock to the apartment, maintains the lock operatable with the key, and provides the key to the tenant. As long as the lease is valid, the tenant can enter the apartment with the key. When the lease expires, the landlord changes the key associated with the lock. So now what happens, a tenant who has the stale key will not be able to enter the apartment. So going by the same analogy, what we are doing is, the lock is the lock assigned to the apartment, and the runtime system is the landlord, and the tenant is the pointer. So when as long as the allocation is valid, the key associated with the pointer is operatable with the lock at the lock location. So in this example, there's a pointer bx2 at location 0xAA. It points to some part in memory which spans from 0xb0 to 0xba. Okay? So it has a key part which is the unique key provided at the allocation time, and it has an address which is the lock. So, and the landlord, which is the runtime system, would have stored the key at the lock location when the memory was allocated. So as long as this allocation is valid, this key associated with the pointer and this key at the lock location would match. Okay? So now when the lease expires, or when the memory is deallocated, all that the runtime system does is changes this key, changes this value to invalid. Any stale pointer will incur a mismatch. Okay? So now, one of the things we pointed out was we don't maintain metadata for everything. We maintain metadata only for pointers in memory. And what happens when you do pointer copies? So let's say one of the common things you do in your code is we have two pointers p and q, you do p equal to q. So operations such as this don't create new metadata, they just propagate the metadata. So how does it look when we just propagate the metadata? Let's say we have a pointer at location bx22 and it points to 0xb5. The first thing to note is this points to the same allocation. This has to have the same identifier metadata. It points to the same allocation. But it points to disjoint parts of the same allocation, so it can have different bounds metadata. So in this case, it's pointing to, let's say this is a structure with two arrays. And this pointer points to the first array, this pointer points to the second array. So they have different base and bounds metadata, but they have the same identifier metadata. Okay? So what do you do on an allocation? Just take the log associated with the pointer and change it to 0. Now this memory is deallocated. Both these are dangling pointers, and when they do the comparison, there will be a mismatch. Okay? So what have we done? What have we accomplished with this lock and key checking? And this was used by various schemes, like Patil and Fisher was the first proponent, and then MSCC by Shaker et al. Used it. And we have inherited some of these techniques in our compiler implementation. So what have we done? What we have accomplished in this scheme is we have changed the hash table lookup, into a sequence of 3 instructions. Earlier, before every memory access, we had to do a set lookup. Now all you need to do is you need to load from this location, and then you need to do a comparison, and then you need to do a branch. So we just have 3 instructions for every identifier chain. So this is just a compare and a load. So it looks much more cheaper, right? On a machine with 6-way ILP, you can execute it efficiently.
Space overhead?
Pardon?
What is the space overhead?
So the space overhead is a great question. So we said we have a disjoint metadata space, right? So let's say all you're doing is you have one pointer, but you have allocated 4 GB of arrays. An array which is n-mapped a large region, which is 4 GB. So then your pointer is register allocated, space overhead is 0. So you have one slot for this allocation. So it's proportional to the number of pointers that you touch in your program. So number of pointers that are actually resident in memory. So if all you have is just pointers which are in registers, like if you just have a temporary and then it's not stored to memory, this pointer is not stored to memory, then there is zero space overhead. But if you have a linked list, then every next field should have metadata with it. It will have some overhead. So on an average, what we are seeing with this scheme is about 34 to 54% space overhead. There are applications such as MCF. It's one application in the spec benchmark suite where we see about 200% overhead. But there are applications where there is like, there's a game called Go. I don't know how many of you are familiar, but it has about like 2% memory overhead. So it depends. It's bimodal and it depends on the application.
Excuse me.
Yes.
So this extra space to store key has to be like allocated by the programmer who wrote this allocator.
Now, so it's done by the runtime. The programmer, there are two players, right? One is the application developer, and then there's a runtime system. It will typically be part of your libc. Like you do a malloc, the runtime does this, and like or there's a transformation. When you do a plugin, there's a runtime library which does this checking. So it will be part of it.
What if the programmer writes his own allocator?
So again, if the programmer has its own allocator, you have to provide hooks to the system. Otherwise, the checking will be done at the larger granularity of the allocation.
So, how is this pointer associated with this metadata? Like, if we are dereferencing a pointer, how is what metadata to access? Like, there are going to be many.
So the whole operation is, let's take an environment where you have every pointer. When you have like p is equal to instar p is equal to malloc of something, it gets it metadata. So p is equal to p of metadata, p of bound is equal to the allocated region plus the size of the allocation. P of key is equal to get new key. P of lock is equal to get new lock location. And now this pointer is in register. When you do a malloc, the return value of a malloc is in a register, right? It's in a register. The pointer is in a register. When you store something into the metadata space, like let's say you store a pointer, like let's say your q is equal, q is a double pointer, and so let me use the plane. Let's say so if you just have this, okay. So this pointer is register allocated. So and its metadata will also be in registers. And your underlying register allocator will either spill it if there was not enough registers and do the restoration. But let's say you do this. Okay? So Q is also a pointer, but you're also storing a pointer into this pointer. So first there's a dereference, you need to do a check for Q. In this case, Q does not have any metadata. Whenever you have a declaration for metadata, it will be there's some default metadata which is null, which will raise an exception. And then you're storing a pointer. So you also store the metadata into the metadata space. So your Q will lie. This is your memory. Let's say Q lies here, it points to P. So at this location, you have the P's metadata. So this is Q, and this points to P, right? This is some object here, malloc region. So here you have the metadata, and this is P's metadata: P base, P bound, P key, and P log. So every time, the semantics is every time you do a pointer load, you load the metadata from the metadata space, and you just propagate it. So you have a compiler transformation or a hardware which actually propagating the metadata.
So there will be two copies of that same metadata, or like it will be used by
So if you have two pointers, let's say there's a pointer pointing to some malloc region, and then you're doing R is equal to P, Q is equal to R equal to Q is equal to R. So you have two copies of the metadata. So every pointer has a metadata. So then you can do copy elimination, you can do fancy things. So those are just optimizations on top of it. Okay, so what have we seen? So we have seen we have to have pointer-based checking with bounds and identifier metadata to provide comprehensive memory safety, right? So you can detect all errors with it. So now we have to implement it. So where can we implement this? So one of the reasons, there was a nice systemization of knowledge paper in Oakland 2013, which surveyed all the memory safety techniques and found pointer-based checking with bounds and identifier metadata can provide comprehensive protection against all use-out-of-free errors and bounds errors. So now we need to implement this. So you need to, the first task in implementing this is you need to identify pointers. So let's say if you're going to implement this in hardware, within the hardware using some scheme. So the pointer has to, the hardware has to identify pointers. So it can be done. So Valgrind tries to do this. Like if you're trying to do this within Valgrind, you'll have to identify pointers. Identifying pointers in binary is a hard thing, right? Binaries lack information about pointers unless you have typed assembly or some complicated structures associated. On the other hand, compilers have pointer information all the time. Compilers perform semantics preserving instrumentation. They have this information. Then you have to inject this operation. So as one of you figured out, how are we going to inject? Like whenever you have a malloc, you need to inject extra operations to propagate metadata. So the runtime, you need to associate it with the runtime library, which does this extra transformation. So compilers can easily do this. And as one of you figured out, metadata has, there may be lots of copies. So you need to eliminate copies. Now you can design structures in hardware to do this. In our watch hardware paper, we use register renamer within the hardware to eliminate copies. But with compiler, you use traditional data flow analysis to eliminate copies. And the last thing is you have to perform checks on every memory access. The hardware doesn't know which memory access is, which check is redundant. It has to perform a check on every access. But on the compiler, the compiler has lots of information. If you're performing a redundant check, let's say you have an access. You have something like this, so you're performing a check again. There's no need to, if this point in the program dominates this point, there's no point in performing two checks, right? You know that if this check succeeds, then this will also succeed. So there's no point in doing two checks. You can eliminate many of these checks. And compilers use standard data flow analysis to do such optimizations. And by implementing it within the compiler, we can eliminate many of the checks. But if you use a traditional x86 instruction, you have to check whether the pointer is less than the base, pointer is greater than the bound. There's lots of instructions, 5 instructions. And then you have to map the metadata space. So you need to do some translation, and then you need to perform loads. This is over it. So what we are saying is, if you have the compiler can perform this task efficiently. Rather than using Valgrind, use the compiler to perform these tasks. And one of the drawbacks of compilers, you'll have some overhead compared to some hardware which will do these checks in a single instruction. Let's leverage the hardware to perform these checks. So what we are proposing, the latest result is hardware-based acceleration or compiler-based checking. Leverage the compiler, let the compiler do all the work. And hardware provides 4 acceleration instructions. How many of you use Valgrind? Okay, if you're not using Valgrind, you should be using it to check all your programs. So, running Valgrind is 30x overhead. Like if you do comprehensive checking, it's 30x overhead. So this means that you have a program that's running for 1 hour, it will take 30 hours. Now if you use the compiler, it reduces to 2 hours. Now when you combine this hardware and the compiler, it reduces to 1 hour 15 minutes. So it's a order of magnitude difference. Imagine you are writing simulators and you want your simulator to be memory safe, and you have critical software you want them to be memory safe. Leveraging the compiler and providing some hardware acceleration will accelerate this job easily. So what we are proposing is 4 new instructions. One is, you saw all these operations. One is a bounce check instruction, a user for free check instruction, a metadata load, and a metadata storage. Okay? So what we saw, there are 4 pieces of metadata with each pointer, right? Now there are 2 options. We can maintain them as 4 different parts in 4 different registers. So then, on your x86 machine, there are only 16 registers. If you maintain 4 pieces in 4 different registers, if you have 4 pointers, you're going to split them. So now the question is, do you want to do this? And if you take an architecture course, you also realize your modern processors have only 2 ports, or 2 load ports and 2 store ports. If you're performing 4 loads, you're going to require 2 cycles to retrieve the metadata. So, but modern machines have something known as 256-bit registers. How many of you have used AVX extensions? Okay, so at least one. So AVX is a 256-bit register in your system. It performs a wide load. If you want to load 4 things and if you perform the same operation on them, you can perform it very quickly. So you don't have to do 4 loads, you do a single wide load. Latency is higher, but like you don't have to, anyway you don't require the data quickly. So use the AVX register, the wide registers in your system, pack the metadata together. So it reduces the register pressure, it avoids splits. And now all you need is propagate the metadata with some compiler optimizations, perform the checks, and you're all set to go. And this is the approach which is adopted by the Intel's latest NPX extensions. Okay, just to give you some idea. So you have an integer which is being loaded through a dereference of a pointer. This pointer q is in a register, right? So the first there are 2 checks you need to perform. The first check you need to perform is you need to ensure that the pointer is not less than the base and the pointer is not greater than the point. So you also have the size of the access to ensure that you are not accessing, let's say you have an allocation which is 400 bytes and you're not accessing, so you have an allocation, this is a character and you're not accessing an integer out of it. So you need to have the size of the access also incorporated in this. And in our x86, in our compiler implementation, this is approximately 5 instructions. And we eliminate this by a single spatial check instruction. It internally supports all addressing modes, encodes the check, and as latency is not critical, since we decouple these instructions from the rest of the instructions, this instruction does not produce a result. And the rest of the instructions can execute. If you have a hardware which has which has a reorder buffer of 128 instructions, these instructions don't influence the dependence in your program. So latency of this instruction is not critical. So, and the other check we need to perform before this memory access is we need to do the lock and key checking, which is 3 instructions. You have the key associated with the pointer and you perform a load from the lock associated with the pointer. If it's not true, you need to abort it. So this is approximately 3 instructions, and we provide a single temporal check instruction, which internally cracks into 2 operations, and latency is not critical again. And the other 2 instructions are metadata loads and metadata store. When do you perform a metadata load? When you are loading a pointer. So Q is a pointer to a pointer, and P is a pointer. So you are dereferencing Q to obtain a pointer. In this case, the compiler implementation would load the metadata by performing a table lookup. Like you can maintain a hash table for the disjoint metadata space or some data structure to maintain the disjoint metadata space, and you perform a table lookup. And similarly, when you do a store, you store the metadata into the table data structure. So this is approximately 14 to 16 x86 instructions for performing this. So by providing a single metadata load instruction, so you perform a wide load. The instruction internally does the address translation and avoids the instruction overhead. And similarly, you perform the metadata loads, and you avoid metadata store, and you avoid the instruction overhead. So what we are saying here is, this is similar to adding an SSE to each instruction. And with Intel or any other vendor frequently adds SSE extensions. Just provide these extensions and leverage the compiler. You can retrofit a comprehensive memory set. So how do we perform this transformation? You have your, we use the LLVM compiler. LLVM is an industrial strength compiler. If you're using a MacBook or if you're using any Google products other than the mobile devices, most of your software toolchain is compiled using LLVM. So it has a front end. The key component of LLVM is the intermediate representation, and it performs lots of optimizations of over this intermediate representation and generates code for various targets. So what we are doing essentially is defining this memory safety transformation within the compiler and operating on this intermediate representation, and then generating the eventual code. So if your code, if your program has a memory safety error, it would trigger an error when the program is actually executed. So to do this, you need some semantics for the LLVM intermediate representation. And then you need to define your memory safety transformation using the semantics. Okay? And then you need to show why your transformation is correct using the semantics. And since you're leveraging a traditional compiler, so you can perform lots of check optimization using standard optimizations available in your compiler. So one of the key things to take away is you have your C code, you're optimizing this using traditional suite of optimizations, and then you are performing the instrumentation using the semantics, and you're optimizing it again. This optimize instrument optimize is a powerful paradigm which can leverage which can reduce the overhead significantly. So you can be totally dumb when you leverage the compiler and still provide comprehensive memory safety. Okay, so this is all cool. So what we have shown is we have 4 instructions and compiler doing the transformation, and you can provide memory safety. Okay, so this is research work, but Intel has recently announced memory protection extensions, which is an ISA specification. Intel adopts the exact same approach. We have been talking with Intel for a long time, and they have internally adopted this scheme, and they are using pointer-based checking. They also use disjoint metadata. They also provide a hybrid scheme. But currently Intel is only providing support for protection against use of the Intel is providing support for protection against bounce overflows. So the key difference between our scheme and the Intel's APX extensions is it does not provide protection against use-of-free errors. And so one of the things Intel had to deal with, or any hardware vendor has to deal with, is backward compatibility. So any software vendor, any software uses lots of libraries, and some of these libraries may not be compiled with these extensions. Now if you make a call there and get a pointer from there, you still should not raise an exception, right? So backward compatibility is an important feature. So Intel has a nice trick where they maintain the pointer along with the metadata in the metadata space and revalidate the pointer to ensure that they are compatible with uninstrumented code. So we are collaborating with Intel to add use-of-free checking in the next generation. So only time will tell whether we'll be successful or not. So now the question is, I've been demonstrating that our compiler is so useful. How much overhead do we get, and what are the benefits of, and what are the remaining sources of overhead? Why are we saying 0%? Why are we not seeing 0% overhead? So in this graph, I'm showing the overhead of a memory safety transformation over a baseline which runs like O4. How many of you have heard O4? So O4 uses aggressive link time optimizations. O3 does typical Metadata-based optimizations. O4 does link time optimization. So baseline is set of specs 2000 and 2006 C benchmarks, and since this is performance overheads, lower bars are better. Okay, so we have both results: timing simulations of an x86 out-of-order core, and for compiler implementations, we run it on stock x86 hardware, which is Sandy Bridge based. On an average, we have an overhead of about 90% for a compiler only implementation. And when we add hardware instructions, we reduce this overhead to 29% on an average. But this is still not zero, right? So what are the remaining sources of overhead? So let's look at what are the remaining instruction overheads in this, among the instructions remaining in the program. So since this is instruction overhead, lower bars are better again. So let's look at the last bar here. So this is a stacked graph which shows the instructions that we added. There were 4 instructions which we added, and then there are some other instructions which have extra overhead, since we are performing it technically. If you look at it, the new added instructions account for significant percent of the overhead. This means that we have reduced, for example, metadata store was 16 instructions in a compiler implementation. By providing these instructions, we have reduced their components to just this. So now let's say we design the next aggressive check elimination algorithm. These overheads will shrink further. And again, if you see, there is a LEA component. So we inserted checks by using inline assembly. So the inline assembly was not using all the addressing modes,